Well, welcome everyone to our webinar today, Accelerating AI While Simplifying Your Storage. My name is Walter Hinton. I'm Director of Product and Solutions Marketing at Pavilion Data Systems, and I will be your moderator today. Joining me are Reggie Reynolds, Principal Product Marketing Manager from NVIDIA, as well as Keith Parker, Director of Product and Solutions Marketing at Pavilion. This event is being recorded, and we will post the event as soon as possible after the webinar has closed. A little bit Zoom dependent on that, so at a minimum, look for it tomorrow. And as we go through, please, if you have questions, enter those through the chat panel, and we will collect them and make sure to answer your questions once we've completed the presentation. So without further ado, I'll turn it over to Reggie and then to Keith.
All right, well, thanks, Walter and Pavilion for hosting this event and inviting me to share. I also want to thank our guests for attending today. I'm Reggie Reynolds, Product Marketing Manager at NVIDIA. I've been in the data storage industry for a long time, starting back in the parallel SCSI days, and I won't mention how long ago that was. I spent most of my early years as a firmware engineer and later managed technical support and engineering teams for companies such as LSI Logic, Sun Microsystems, now Oracle, and Seagate, and most recently DDN Storage. Along with all other areas of technology, storage and networking has advanced rapidly, especially in the last decade or so. I'm going to focus my presentation on these two technologies that facilitate the movement of I/O to and from storage solutions, and then turn it back over to Keith and Walt, well, in particular Keith, who will describe how they're taking advantage of these technologies to exploit the performance of their solutions. Next slide, please. So a while back, scientific computing primarily consisted of first principle simulations and basic image analysis in a centralized computing facility. Today, researchers and data analysts are fusing traditional simulations with deep learning, big data analytics, and streaming edge computing to solve the mysteries of the world. It is the newest trend of what we refer to as data-driven scientific computing. We're also utilizing higher fidelity sensors and executing larger scale simulations both at the edge and in the data center. And that, of course, has created huge data sets needing to be processed as quickly as possible for insights in solving highly complex problems. To process these larger data sets, the data has to move from point to point as fast as possible. And depending on the complexity and topology of the network, the data could take multiple hops to get to its destination, creating the need for very low latency. Because of these requirements, NVIDIA invested in a network technology from Mellanox called Infiniband. Next slide, please. Thank you. Now, Infiniband primarily consists of two types of services, network and computing. First, from a networking perspective, Infiniband has the highest throughput. For example, for over 2 years now, we've delivered 200 gigabits per second HDR, and soon to release 400 gigs per second NDR, which I'll talk more about later. It is the lowest latency network in the market, and Infiniband comes with a unique network features such as quality of service, adaptive routing, and congestion control. Here's something I learned recently that I thought was really cool, is that Infiniband from the beginning was architected to support native hardware RDMA to achieve the highest performing by moving data between devices without CPU intervention. This technology is the foundation for GPUDirect RDMA, an amazing feature that we'll go into more detail later. The second set of services that is most interesting is the ability of Infiniband to provide in-network computing. These are computing engines that sit inside of the silicon devices of the Infiniband network in both the network cards and switches. These computing engines provide pre-configured and programmable services for acceleration of I/O and offloading of services that normally run on the server. Next slide, please. Although we mostly focusing on the enterprise AI on enterprise AI this session, it is important to note that Infiniband has been widely accepted in the high performance computing and supercomputing industry. This is a group there is a group out there that tracks the fastest computers in the world, and they organize them in a list called the top 500. As you can see from this slide, these are very powerful computers with tens to hundreds of petaflops of processing power. And there's a couple of examples of exaflops as well. 7 of the 10 fastest computers in the world use InfiniBand networking. That's very impressive. Next slide, please. I like this slide. By the way, I would like to give credit for this slide to my colleague at NVIDIA, Kushal Datta, as it really fits our discussion today. Why 21 zeros? Well, as we all started to work from home last year due to the pandemic, cumulatively we generated and recorded around 64 zettabytes of data. That's 10 to the 21 bytes. And according to my Xfinity bill, I think my household used a pretty good chunk of that. Even though my career has been mostly in storage industry, I'm still amazed at how radically we have improved data collection, storage, and processing. When I was growing up in the data storage world, gigabytes was a big deal. And again, no discussion about age here. But now we're talking zettabytes. That's amazing. We're in the age of data, and it's not ending anytime soon. And as the world trends towards more digitalization, we're going to continue surpassing all previously predicted data generated on the planet. Next slide, please. But of course, we're not stopping at 64 zettabytes. And I'm sure my Xfinity bill won't be slowing down either. The rate at which we generated and collected data is only going to increase. And I'm sure in a year's time, one of you will look at this chart and tell me I was way off, that we've produced 100 times more data than what your chart is showing. And we're not collecting all this data just to store it in a corner. We're using it in AI, deep learning, and machine learning to break the boundaries of science and do things we have never imagined we could do before. Just look at the speed with which we were able to explore protein and chemical combinations to create COVID-19 vaccines. That was actually remarkable. So all shows we are moving towards a future where new scientific breakthroughs will be fueled by the explosive growth of scientific data. Next slide, please. And yes, extreme scale AI means extreme scale data, and both need extreme IO. At the center of acceleration of AI has been the GPU. We want to ensure that you maximize your investment in your GPU infrastructure, your data scientists, data sources, and ingestion. And to make that happen, the data infrastructure needs to deliver IO at a high enough level to saturate the GPU to use its cores at their highest efficiency. And as the computing power of the GPUs increase, this becomes a bigger challenge because IO latency becomes a dominant factor. And as the data sets continue to get larger, you need higher throughput to move that data to the GPUs. InfiniBand is the high bandwidth, low latency network architecture that connects compute to storage to ensure you're fully saturating your GPUs at scale. Next slide, please. As I talked about earlier, already InfiniBand is the network of choice for data-intensive simulation and analytic applications in HPC and supercomputing. It remains the most efficient way to move data using fundamental concepts of hardware RDMA, delivering at the highest performance and the return on investment at any scale. By bringing additional network engines and capabilities closer to the memory and offloading more tasks from the compute and onto the network, we now have a smarter, more capable, and the most efficient network solution that can participate in application runtime. InfiniBand is the optimal and ultimate software-defined network with complete centralized management. Also, InfiniBand is an open standards-based technology, so therefore compatible with its previous and future generations, and thus preserving your capital and resource investments. Next slide, please. Let's look at each of the components that form the entire end-to-end InfiniBand infrastructure between compute and storage. by starting with the ConnectX-6 InfiniBand adapter card. These adapters support HDR 200 gigabits per second and support PCIe Gen 4. They're also RDMA optimized and support in-network computing plus storage, cloud, and security offloads. And then there's the Bluefield Data Processing Unit. It is relatively a new addition to our portfolio. It provides a high-performance programmable network engine with the ConnectX-6 chip coupled with ARM CPUs to enable the customization and optimization of both control and data path operations. Along with the DPU, there's an NVIDIA software development kit that enables developers to easily create high-performance, software-defined accelerated services, leveraging industry standard APIs for storage. And then the Quantum InfiniBand switches deliver a complete chassis and fabric management solution to provide cost-effective and scalable switch fabrics, ranging from small clusters up to thousands of nodes, reducing operational costs and infrastructure complexity. With the ability to provide 80 HDR 100 gigabits per second ports, it allows storage vendors such as Pavilion to create a very high density storage cluster. To create very high density storage clusters. And lastly, the LinkX cables provide an industry low bit error rate, lower latency, and lower power for superior connectivity. Next slide, please, Keith. Thank you. To complete the InfiniBand portfolio, we have the appliances starting with the Metro X2 long haul InfiniBand switch that seamlessly connects your InfiniBand storage solution to data centers up to 40 kilometers apart. We can also provide simple integration to Ethernet, to external Ethernet fabrics via the Skyway Ethernet gateway. And lastly, the Unified Fabric Manager software and appliance is an enterprise classic fabric manager that combines telemetry, analytics, and preventive troubleshooting at scale. Next slide, please. Go to the next slide, please. Sorry. Oh, sorry. I'm sorry, Keith. You can go back.
No worries.
Got a little confused there. Thank you. Okay, InfiniBand will continue to lead the networking with our upcoming release of NDR 400 gigabits per second technology. We're scheduled to release samples by the end of this year, and volume availability of these network components will be happening by early 2022, with both the adapters and the Bluefield DPU supporting Gen 4 and Gen 5 PCI architectures, as well as advanced ConnectX-7 in networking computing features. Our Quantum 2 NDR switches will support 64 ports of 400 gigabits per second in InfiniBand, or 128 ports of 200 gigabits per second in a 1U chassis, significantly reducing the cost of network design and topologies. All right, next slide. We meaning NVIDIA, InfiniBand will continue to set world records in the industry with double the throughput, 4 times of MPI performance with new all-to-all in-networking acceleration engines, improve total cost of ownership with 4 times more switch capacity, and be exascale ready with 6.5 times higher scalability, and 32 times AI acceleration with updated in-networking computing technology. Next slide, please. Now, accelerated networking computing requires accelerated I/O to maximize the performance. And with NVIDIA Magnum IO, it is the software library that is used by the developers to deliver parallels, asynchronous, intelligent data center I/O, maximizing your storage and network performance for multi-GPU and multi-node acceleration. Magnum IO is a fully optimized software development kit, or SDK, that takes full advantage of your DGX A100 platform the Infiniband network, and the high-performing storage solutions such as pavilions. The Magnum IO SDK is part of the CUDA software ecosystem and includes GPUDirect Storage, which I'll explain a little bit more on the next slide. Next slide, please. Now, GPUDirect is a direct path between the external device such as storage and GPU memory. Faster GPUs are increasingly starved by slow I/O, and time spent loading data impacts application performance. In multi-GPU based servers such as the DGX A100, the CPU's single thread performance is in the critical path of data access from local and remote storage devices. Now, as you can see on the left side, the data packets are going to the network from an external device such as storage. Then it's moving from the network card to the host memory, and finally from the host memory to the GPU memory. With GPUDirect, now looking on the right, the data packets move directly to the GPU memory, now bypassing the CPU and the host memory, avoiding multiple copies through the bounce buffer in CPU memory. GPUDirect technology provides lower latency, higher bandwidth, and reduced CPU utilization. And Keith will be showing more details on the benefits of GPUDirect and RDMA with the pavilion storage solutions. Next slide. We've been iterating engineering releases to our storage partners with GPUDirect Storage, such as Pavilion, for some time, and wanted to make sure that you guys know that we've recently, a couple of months ago in June, announced a production release of GPUDirect Storage on DGX A100 platforms. GDS comes as part of the Magnum IO accelerated software stack that we discussed earlier, and is integrated into the CUDA 11.4 toolkit. CUDA, by the way, is development environment for creating your GPU applications on NVIDIA GPU-based platforms. GDS, or GPUDirect Storage 1.0, is going to support does support DGX-based OS 5.0, Ubuntu 18.04, and Red Hat 18.3 OS releases. For additional details on the GDS and our NVIDIA on GDS and our NVIDIA Infiniband, please reach out to me. My email address is reggier@nvidia.com. That's Reggie, R-E-G-G-I-E-R. Thank you very much. And I'll pass this back over to Keith. Thank you.
Thank you, Reggie. Really appreciate that. Great job. And as we look to accelerate AI and really any of the modern applications that are driving us forward today, what we need to do is recognize that these are all data-driven applications, meaning that they are truly enabled by massive volumes of data. And that certainly includes AI, whether you're talking about deep learning, which relies on huge volumes of data for model training, natural language processing, which needs to process massive volumes of data quickly, or recommender engines, which, at least according to my credit card bill, do such a good job of suggesting additional things we might want to buy before checking out online. All of these are going to be reliant on moving and processing incredible volumes of data at ever-increasing speeds. And this is true of other applications as well, such as media and entertainment, which is constantly faced with the need to capture video with ever greater resolution and then move that data for processing, or virtual environments. And let's be honest, in today's world, all environments are virtual environments, where accelerating the flow of data with greater efficiency means you can do more with less hardware and software, which in turn reduces both management and licensing costs. Facial recognition relies on ingesting huge volumes of video data and then processing that data using analytics to improve security. And big data analytics and business intelligence applications, those work by moving and processing huge volumes of data so that organizations can make better decisions and produce more products, better products in less time. And of course, life sciences, with the ability to deliver better treatments, is top of mind for all of us these days. And these are just some examples of the modern applications which we all take for granted, which are truly enabled by massive volumes of data. And all of this has been enabled by the rise of GPU-based computing, which has enabled massive gains in the ability to process data that could have never been achieved if we were still reliant on CPUs alone. Yeah, as we all know, Moore's law, with its historical constant increases in performance, has diminished recently. But GPUs have taken over and delivered incredible performance gains beyond what is possible with CPUs. GPUs have powered this revolution because they enable data to be processed with incredible parallelism. And when you look at a single CPU core, it's going to be faster than a single GPU core. But whereas CPU might have 64 cores, GPUs will have thousands and thousands of them. And this in turn enables GPUs to process data in parallel, delivering incredible performance so that those data-driven applications we talked about can do the things that we need them to do. Now, this takes us to the next step on our journey. And this is an old quote from Kent Batcher, who was a famous data scientist, who once said, "A computer is a device for turning compute-bound problems into IO-bound problems." And he said this somewhat tongue-in-cheek, but it was true then, and it's still true today. The thing is, as systems become able to process more and more data, the challenge becomes moving that data into and out of those compute systems, in this case, the GPUs. GPUs have revolutionized how quickly data can be processed, but they can only deliver on the promise of that processing performance if they are fed the data they need to do that processing in a performant and efficient manner. There we go. And the application vendors agree. These are just two examples that I took, but you can find similar quotes from most major application providers. Here we have quotes from Microsoft and from Splunk on SQL and Splunk, obviously. And according to Microsoft, any server that hosts SQL needs to have the fastest possible response time from the IO subsystem. And you cannot add other resources to compensate for a slow IO system. And Splunk says, they recommend storage with very high numbers of random IOPS, IOs per second. And this is really critical. What they're essentially saying is we need fast IO, meaning high IOPS, and extremely low latency. And there's one more piece to the puzzle that we need to address, and that is data ingest or storage write performance. We all know that data is being created at an incredible rate, whether it's log data or sensor data. It could be data coming from a satellite or a video feed, machine generated and IoT data. There's literally 1,000 different ways that data is being created, driving volume and velocity. To handle that data creation requires what most storage providers don't like to talk about, which is write performance. The need for high write performance has never been more important, and yet most storage vendors don't even publish it when it comes to their products. Now, I'm going to go on a limb here and suggest that if these vendors don't tell you the write performance, there's probably a reason for it. So just to recap, what we need is high IOPS, so we can give those GPUs the data they need to process. We need the ultra low latency, so those GPUs can get that data as quickly as possible, and high write or data ingest performance, so the storage system can bring all that data in that is being created, and you don't have to do data sampling and pick and choose between what kind of data you want to keep. And now this brings us to a quote from Gartner. Now, I don't like to read slides, but I will here just because I think it's so important. And that's next generation data-centric workloads like artificial intelligence, modeling, and simulation require bandwidth, latency, and IOPS beyond what the capabilities of NVMe technology-enabled dual controller scale-up all-flash arrays at scale. So essentially what this is saying is the standard model for storage systems can't deliver on the needs of these applications. Now, I'm gonna be in danger of dating myself like Reggie did, and I go back to the old parallel SCSI days too. I remember setting up those SCSI cards with jumpers, so I've been there. And in all that time, storage arrays, their basic fundamental architecture, it hasn't changed. It's based on a dual controller array, where each controller is essentially a self-contained server with a CPU and networking and memory and OS and software. and it's clustered together with that other controller. So it's a dual server cluster. And you never get the full performance of both of them because that second server is really there for redundancy. So you're going to get the performance of one of them, whether it's active, 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 passive, however you've got it controlled. And what it's going to do is it's going to give you the performance that that single controller can provide. And what's needed is something that can go beyond that to really move the data and provide the high IOPS, the low latency, and the right performance that these applications need today. And that takes us to Pavilion. And when Pavilion created our solution, we really looked at that challenge and saw how storage had not really changed over time. With still that same dual controller architecture. Sure, the interfaces have changed, and we've gone from SCSI to SAS and fiber channel. We've gone from spinning disk to SSDs, but the underlying fundamental architecture hadn't changed. And so Pavilion took a fresh approach, and we based our system on the fastest thing in the data center, which is the network. And so we based our system not as a server cluster, but on a switch-based architecture. We have a 6.1 terabit per second PCI non-blocking switch-based architecture. And what that enables us to do is deliver massive performance, massive scale, and massive capacity. So what do I mean by that? Well, we have up to 72 NVMe drives in each given system, which given today's current drive capacity means we can support over 2 petabytes per system. We're not limited to a dual controller solution. Instead, we have up to 20 independent storage controllers per system. So it's 20 controllers with their own, each with their own CPU, network, memory. So you can get the performance of not 2, but 20 controllers. We support Infiniband for that high performance, secure, reliable network connection that Reggie talked about. And we also support, Ethernet. That multi-controller architecture allows any controller to talk to any drive, so you're always getting performance, redundancy, reliability. We're a cashless solution, meaning typically the dual controller architecture is going to have a whole bunch of cache, whether it's expensive DRAM or SCM, and it's really in there to provide a high performance tier to give the appearance of high performance to the system. You can get the performance of that cache as long as you don't exceed the capacity of it. Because we have so many controllers, we can write directly to the drives. We don't have to cache it. So you get not just extreme performance, you get it without that limitation. And we can do RDMA. We can do DMA from any drive to any controller, and we do RDMA to the hosts. We have up to 40 connectors, Ethernet or Infiniband connectors per system, and that's all packed into a 4RU chassis. And the result is unrivaled performance density. And it's that density that really sets us apart. We deliver incredible performance. And I'm going to be honest, others can match that performance, but it's going to take them racks of storage to do it. We do this with a single system, and that system scales out across systems so you can get more performance as needed. So we talked a little bit about RDMA, and these are the results of testing that NVIDIA did with Pavilion when they looked at using NVMe RDMA versus iSCSI. So essentially moving TCP data using either the iSCSI protocol or simply using NVMe, and the impact RDMA had. And what they found was, using RDMA, we were able to get twice the IOPS at half the latency. And this is using exact same hardware. There were no hardware changes between this. It's very simple to change between protocols with Pavilion. It's literally 2 or 3 mouse clicks, and you can move from NVMe, RDMA to iSCSI or NFS or whatever the protocol you want to use is. Here, for write IOPS, we get 1.5 times the write IOPS at 61% the latency. And the result is, when used in a virtual environment, you can do twice as many virtual machines on the same hardware. You can do it at half the costs. You can run more virtual machines at less latency. You can get more IOs at half the latency and get massive bandwidth for those data-driven workloads that we talked about. So what are the real results? What are we talking about here? So I talk about IOPS, the Pavilion HyperParallel data platform can deliver the 20 million read IOPS and 5 million write IOPS. That's per system. It gives incredibly low latency of 100 microseconds for reads and 25 microseconds for writes. And I want to talk about the fact that that's measured at the host. When I say measured at the host, when you look at latency for most storage solutions out there, what those solutions are talking about is the latency measured from the time the IO request is received by the system until the time the IO request is fulfilled back out onto the wire. So it's latency within the box. What Pavilion is talking about is that same latency within the box and the latency back out across the network until the data is placed into memory at the host. So we're not just orders of magnitude faster, we're orders of magnitude faster over a greater distance. And of course, write performance. We talked quite a bit about how important write performance is to these data-driven applications. Each individual Pavilion system can do up to 90 gigabytes per second of write performance. So massive performance. And we're able to scale up and scale out. That's one of the things that is really enabled by the switch-based design of the Pavilion solution. So in this case, this particular example, we're using file data. So using the Pavilion HyperParallel file system, you can get, you can start off with, in this case, we started off with a quarter of the box, so 500 terabytes. And you were able to get a quarter of the performance, a little under 19 gigabytes per second read and 12.5 gigabytes per second write. And as you scale up within the box, you're able to increase capacity and performance as you scale up. So you can start small and grow as you need. And then of course that scales out across systems as well. So an individual system using the Pavilion HyperParallel file system or a global namespace, the 75 gigabytes per second of read. And every time you increment an additional system, you get the full linear performance of that additional system. And we've proven this out in our labs with up to 8 systems. And it scales linearly. It's not like a traditional dual controller system where every time you scale out an additional system, there's a performance decrease across all systems. With Pavilion, it continues to be linear. And 8 systems gave us 600 gigabytes per second of read, 16 petabytes of usable capacity, and only 32 rack units. And that's not just for file data, that's for object data as well. Using object data, we can do 50 gigabytes per second and 30 gigabytes per second of write performance. Well, that's scaled linearly, 400 gigabytes per second of read performance, 16 petabytes of object capacity. And you can mix and match block, file, and object data across the Pavilion systems in any way and in any configuration. Specifically talking about the NVIDIA solution and how Pavilion works with that. Reggie talked about GPUDirect Storage, and of course, Pavilion has been supporting GPUDirect right up through the release of that. And we are one of the only ones that can actually do block and file performance with GPUDirect Storage. Here we did performance testing using a single Pavilion system, talking to a DGX A100, and you going back and forth between GPUDirect and non-GPUDirect for sequential block reads. We were able to do 91 gigabytes per second compared to 37 gigabytes per second without GPUDirect. And we're able to do that at a fraction of the latency, 2.3 times less latency and 11.5 times less CPU utilization. And those are resources that can go back to application processing. And that held true for writes as well, 75 gigabytes to 38 gigabytes for GPUDirect and non-GPUDirect. Similar performance gains were seen with file, 96 gigabytes per second versus 38 gigabytes per second, 1.75 milliseconds of latency versus 4.4 milliseconds, and massive decreases in CPU utilization, 7.9% versus 24.4%. By taking advantage of NVIDIA's revolutionary GPUDirect storage, you can get huge performance gains, incredibly low latency, and CPU utilization resources back. So what you get with Pavilion and NVIDIA is you get an incredibly dense form factor. You get ultra low latency, impressive write performance, and linear scale out with no host agents required. Beyond that, we can help solve the bigger than memory challenge. So what is the bigger than memory challenge? Well, any system is going to have some amount of internal storage. The DGX A100 has 4 internal NVMe drives with 15 terabytes of internal storage, which delivers phenomenal performance. The challenge becomes, what happens when your data sets are greater than that capacity? Well, you can scale out to the Pavilion HyperParallel data platform, which of course provides linear growth as you need to expand that. So if you can use the DGX A100 to run analysis on last month's data sets, using Pavilion, you can expand that to perform those same analysis across not just last week's data sets, but last 10 years. You can get better analysis of more data with the same kind of performance that you would expect from that internal storage. So you can analyze larger data sets, larger volumes, and get better results over time. So internal storage is perfect for those smaller data sets. Larger data sets are going to require external storage, but you need to be able to achieve the same kind of performance. And the combination of NVIDIA GPUDirect and Pavilion delivers ultra low latency. Infiniband provides that high performance, reliable interconnect between the systems. And Pavilion's unique architecture provides that storage with a massive footprint. Now here's just one example. This is an application called Graphistry. And what it does is it provides a visual analysis of data. So it uses AI to analyze huge volumes of data so that organizations can do things like identify network breaches, find problems before they happen. And it does it in a visual way as opposed to providing a long list of data. And it does this in real time. And with Graphistry, they've done this using Pavilion and NVIDIA. And what they found they needed to be able to move 300 gigabytes per second. So each node needed 23 gigabytes per second. So Pavilion's easily able to provide that. But the data sets were just too big for the internal storage. So what they did is they went with Pavilion. They were able to skip the CPU, utilize GPUDirect Storage, grow the capacity of that system, and manage and analyze huge volumes of data without any degradation in performance whatsoever. And that is ultimately what we're providing. NVIDIA has absolutely revolutionized how data can be processed, what can be done with these applications, and it's all driven by the need for high performance, ultra low latency storage, which Pavilion is able to provide in that total solution. And with that, I'd like to thank you, and we'll move to our Q&A session.
All right, guys. Hey, thank you so much, Reggie and Keith. This was very informative. I personally learned a lot. And we have several questions that have come from the attendees of the event here. So I think, Keith, this one's for you.
Okay.
And what are the limits for your parallel file system in terms of capacity and number of systems it can support?
Well, that's kind of an interesting one. So in terms of what we can theoretically support, it's I don't want to say unlimitless, but for all intents and purposes, it would the mathematical number is more systems than we can build with the resources on Earth. But what we've practically tested in our systems is we've tested up through 8 systems. Is what we've tested, and we've shown that linear scale out. Is at some point, if we need to test more than 16 petabytes, and then we'll absolutely be able to do that. But that's what we've tested so far, and we've seen that linear performance continue for block, file, and object data types.
Interesting. And kind of a follow-up to that, are there differences between the Pavilion parallel file system and other file systems like Spectrum Scale or Lustre?
Well, yeah, there's some differences. Probably the biggest one is going to be cost. The Pavilion HyperParallel file system comes with the Pavilion as a part of the Pavilion HyperParallel data platform. There's no additional charge for that. In terms of features and functionalities and capabilities, it's a file system. It's able to provide all the things you would expect it to do in terms of data management, data access, data security. but really the biggest difference is going to be cost. There's, like I said, there's no additional charge for it. It is just part of the solution.
Gotcha.
And
Reggie, here's one that I think is targeted for you. Do I need special networking to use GDS, or can I use my existing switches?
That's an excellent question. It depends, right? So your switches definitely need to be able to support RDMA, and if they do, then most likely they will be able to support GDS. But if your current switches are from NVIDIA, then that's a definite yes. But we would definitely need to work with you, directly and on a case-to-case basis to ensure that your current network infrastructure is supporting GDS.
Okay. And follow up to that, to take advantage of GPUDirect, can I use any storage solution, or does the storage need to support it too?
And basically your storage needs to support RDMA. As long as it's supporting RDMA, you're going to be able to take advantage of GPUDirect. And and as Keith showed earlier, is that their systems do support that, and of course they're integrated. They've been able to take advantage of GDS as well.
Okay. And I think, Keith, this one comes back to you. Can you explain a bit more about the flexibility to expand the Pavilion system? I can actually grow capacity and performance, sort of scale up and out with both?
That's correct. So with the Pavilion system, I talked about the fact that we support up to 72 drives and 20 controllers, but you don't have to start there. You can start with as few as 4 controllers and as few as 18 drives, and you can scale up within the system, either additional controllers for more performance or additional drive for more capacity, or both, or completely independent of each other. So you can stay with 18 drives and grow up to 20 controllers, or you can stay at 4 and grow up to 72 drives, or whatever meets the performance and capacity needs of your organization. So you have total flexibility in scale up of performance and or capacity within the system. And then you can scale out across systems, and doing that, you can support that using any combination of block, file, or object data. So you can use half of one system for block and then half of a second system for more block. You can put file object across multiple systems. You can do it really in any combination. And we support multiple protocols and data types, and you can mix and match them to your heart's content. That's one of the things that's really unique about the Pavilion system. Is I talked about the dual controller systems being a limitation, and the ability to support multi-protocols is one of them. Now they all support multi-protocols, but the challenge is what you have that one controller running whatever the system was really designed for, and then you've got that other one. We'll say it was designed for file. Then you've got a secondary one such as object running on top of it. Well, you've got object running on top of file. So that's going to impact your performance. With Pavilion, because we have so many controllers, every data type, every protocol is going to run natively on any given controller. We don't have that extra overhead. So you can have 5 controllers dedicated to block performance and 8 controllers dedicated to file, and remaining ones to object, or whatever combination you want to have. So you have total flexibility in scale up, scale out, and in data type support.
And sort of real time, as you were talking, another question, which is what file protocols and versions are supported?
So we support a number of them. So obviously NFS, we do NFS v3, NFS v4, PNFS. We are also able to support SMB. So we can support whatever's really needed. So NFS, SMB are the standard ones.
And I think back to Reggie here. I think I already know the answer, but maybe help us out. It's GDS supported by Rocky.
Yes, it is. With Rocky, or was called RDMA over Converged Ethernet, it is supported, and this because there are switches out there, Ethernet switches that support RDMA, then yes, you can take advantage of GDS with Rocky as well.
Okay. And NDR and InfiniBand in Q1 of next year, Reggie?
Yes, that's what we're committing to. And but you know, with everything that's going on in the world today, who knows if that will actually happen, but that's what we're shooting for.
Okay, and Keith, assuming they hit Q1, how soon will Pavilion be supporting NDR after its GA?
We haven't announced an actual date yet, though I'm sure we'll be supporting it at a reasonable time shortly thereafter.
Fantastic. Well, guys, this was great. And attendees, thanks so much for your questions. If you have other questions, feel free to reach out. Probably best is marketing@pavilion.io, and we will respond in kind. And look for a posting of this event here in the next 48 hours or so. Thanks again, panelists and attendees, and all the best. Cheers.
All right,
Thank
thanks.
you.
Take care, guys. Bye-bye.
Bye.